Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. I have prepared a training course on instruments reactor systems in refineries and chemical plants, which will be beneficial for those who are working in oil and gas refineries and chemical plants. After completing this course, you will be able to describe the function of a reactor. Describe exothermic, endothermic, replacement, neutralization, and combustion chemical reactions. List reaction variables and their effects. Balance a chemical equation. Describe a continuous and a batch reactor. Describe a reactor's function in alkylation. Describe a reactor's function in fluid catalytic cracking. Describe a reactor's function in hydrodesulfurization. Describe a fixed bed reactor's function in hydrocracking. Describe a tubular reactor and chemical synthesis. Describe a fluidized bed reactor in coal gasification. Describe fluid coking. Before starting the course, let us have a look at key terms. Alkylation is use of a reactor to make one large molecule out of two small molecules. Balanced equation is a chemical equation in which the sum of the reactants or atoms equals the sum of the products or atoms. Catalyst is a chemical that can increase or decrease reaction rate without becoming part of the product. Chemical equation is numbers and symbols that represent a chemical reaction. Chemical reaction is a term used to describe the breaking of chemical bonds, forming of chemical bonds, or breaking and forming of chemical bonds. Combustion is a rapid exothermic reaction that requires fuel, oxygen, an ignition source and gives off heat and light. Cracking is decomposition of a chemical or mixture of chemicals by the use of heat, a catalyst, or both. Thermal cracking uses heat only, catalytic cracking uses a catalyst. Endothermic is a chemical reaction that must have heat added to make the reactants combine to form the product. Exothermic is a chemical reaction that gives off heat. Fixed bed reactor is a vessel that contains a mass of small particles through which the reaction mixture passes, also called a converter. Fluid catalytic cracking is a process that uses a fluidized bed reactor to split large gas oil molecules into smaller, more useful ones, also called cat cracking. Fluid coking is a process that uses a fluidized bed reactor to scrape the bottom of the barrel and squeeze light products out of residue. Fluidized bed reactors suspend solids by countercurrent flow of gas. Heavier components fall to the bottom, and lighter ones move to the top. Hydrocracking is use of a multistage fixed bed reactor system to boost yields of gasoline from crude oil by splitting heavy molecules into lighter ones. Hydrodesulfurization removes sulfur from crude mixtures. Material balancing is a method for calculating reactant amounts versus product target rates. Neutralization is a chemical reaction designed to remove hydrogen ions or hydroxyl ions from a liquid. Products are the end results of a chemical reaction. Reactants are the raw materials in a chemical reaction. Reaction rate is the amount of time it takes a given number of reactants to form a product or products. Regenerator is used to recycle or make usable again contaminated or spent catalyst. Replacement reaction is a reaction designed to break a bond and form a new bond by replacing one or more of the original compound's components. Stirred reactor is a reactor designed to mix two or more components into a homogeneous mixture, also called an autoclave. Tubular reactor is a heat exchanger in which a chemical reaction takes place, used for chemical synthesis. Introduction to reactions. A reactor is a vessel in which a controlled chemical reaction takes place. This chapter discusses 5 basic types of reactors: stirred tank reactors, converters or fixed bed reactors, fluidized bed reactors, tubular reactors, and furnaces. There are many other types of reaction vessels, however, most of them are simply combinations of those 5. The various things that have an effect on a chemical reaction are called reaction variables. The design and operation of a reactor depend largely on how variables affect the chemical reaction that is taking place in the reactor. For example, heat increases molecular activity and enhances the formation of chemical bonds, and pressure increases atomic collisions. Other factors that affect chemical reactions are time, the concentration of reactants, and catalysts. Temperature. In a reaction mixture, gas, or liquid, the temperature determines how fast the molecules of the reactants move. At a high temperature, the molecules move rapidly through the mixture, colliding with each other frequently. The more often they collide, the more apt they are to react with one another. A good rule of thumb for chemical reactions is that the speed with which two chemicals will react doubles for each 10 degrees Celsius increase in temperature. This rule assumes, of course, that other variables do not change. For example, if 10% of the chemicals in a reaction form product in 1 hour at 50 degrees Celsius, then 20% will form products at 60 degrees Celsius in 1 hour. The danger in this type of reaction is that twice as much heat will be given off at the higher temperature. If the extra heat cannot be removed from the reactor as fast as it is formed, the temperature will rise, causing the reaction to proceed at even higher rates. Obviously, you will soon have an uncontrollable reaction and, possibly, an explosion. Pressure. The effect of pressure on a reaction cannot be generalized as easily as the effect of temperature. In a liquid phase reaction, pressure can increase or decrease the reaction rate, depending upon the readiness of the reactants or products to vaporize. In a gaseous reaction, pressure forces molecules closer together, causing them to collide more frequently. In other words, the higher the pressure there is in a gaseous reaction, the higher the reaction rate. Reaction time. Reaction time is simply the length of time that the reactants are in contact at the desired reaction conditions. Contact time refers to the length of time the reactants are in contact with a catalyst. Residence time refers to the length of time reactants remain in a tank before forming a product. Generally, the longer the reaction time, the more products are formed in the reaction. This does not necessarily mean that it is desirable to let a reaction continue for a long time. Concentration of reactants. The concentration of reactants in the reactor has a major effect on how fast the reaction will take place, what products will be produced, and how much heat will have to be added to or taken away from the reaction. We generalize here for the sake of simplicity and say that for most reactions, the higher the concentration of reactants, the faster the reaction and thus the more heat that is generated or needed. Agitation provided by mechanical agitators or by the turbulent flow of the reactants may affect concentration. In general, good mixing or good agitation produces an efficient reaction with the desired products. Poor agitation may produce pockets that have a high concentration of one reactant and low concentration of the other. This uneven distribution may produce undesirable as well as unpredictable products. Catalysts. Many chemicals will not react when placed together at high concentrations and heated or will produce unwanted products. Therefore, an additional substance called a catalyst is added to stimulate the reaction and to produce the more desirable product. Most catalysts do not react with the reactants, so usually they can be reused several times until they become dirty or ineffective. Then they must be replaced or regenerated in some way. Other types of catalysts, usually liquids or gases, will react with the reactants, forming an intermediate product. The reaction will continue until the desired product is formed, releasing the catalyst to be used again. It is not unusual for some catalysts to be destroyed in the reaction or discarded because of the difficulty of recovering them. Catalysts can be classified as adsorption, intermediate, inhibitor, or poisoned. An adsorption-type catalyst is a solid that attracts and holds reactant molecules so a higher number of collisions can occur. It also stretches the bonds of the reactants it is holding, thereby weakening the bonds, which then require less energy to break and rebond. An intermediate-type catalyst forms an intermediate product by attaching to the reactant and slowing it down so collisions can occur. An inhibitor-type catalyst is any substance that slows a reaction. A poison catalyst is one that no longer functions or is used up. Inhibitors. An inhibitor is a substance that prevents or hinders the reaction of two or more chemicals. Sometimes, trace amounts of impurities in the feedstock to a reactor kill a reaction or severely reduce the amount of desirable products formed. The inhibitor may hinder the reaction by reacting with some of the raw materials before the desired reaction can take place, or it may react with the catalyst, making it unstable. Exothermic and endothermic reactions. Exothermic reactions are characterized by a chemical reaction accompanied by the liberation of heat. As the reaction rate increases, the evolution of heat energy increases. Controlling reactant flow rates, removing heat, or providing cooling can control exothermic reactions. This type of reaction is subject to runaway if sufficient heat is not withdrawn from the system. Endothermic reactions absorb energy as they proceed. They must have heat added to form the product. Replacement reactions. Industrial manufacturers use replacement reactions to remove dissolved mineral ions from process water. A number of dissolved minerals can be found in process fluids. A common compound found in process water is calcium chloride. Calcium chloride forms positive calcium ions and negative chloride ions when it is dissolved in water. A replacement reaction can remove the calcium ions and the chloride ions with synthetic resins. Resins come in a variety of shapes and designs. Sometimes resins take the form of plastic strands rolled into balls and charged with ions. A hydrogen ion on a resin ball is replaced by the calcium ion as the process fluid moves through the resin bed. The replacement reaction will take place until all of the calcium is removed from the fluid, or the hydrogen ion is used up on the resin balls. Resin balls can be treated with positively or negatively charged ions and used for replacement reactions. For example, resin balls charged with hydroxyl ions can be used to replace the chloride ion. Neutralization. Neutralization reactions remove hydrogen ions, acid, or hydroxyl ions, base, from a liquid. Neutralization reactions are designed to neutralize the acidity or alkalinity of a solution. Hydrogen ions and hydroxyl ions neutralize each other. Combustion. Combustion reactions are exothermic reactions that require fuel, oxygen, and heat. In this type of reaction, oxygen reacts with another material so rapidly that fire is created. For example, the reactions in a fired furnace or a boiler are combustion reactions. Natural methane gas, fuel, is pumped to the burner, mixed with oxygen, air, and ignited heat. This reaction, which releases carbon dioxide, CO2, and water, H2O, can be represented by the following chemical equation. CH4 plus 2O2 reacts to give CO2 plus 2H2O. In this equation, one molecule of methane, CH4, chemically reacts with two molecules of oxygen to produce one molecule of carbon dioxide and two molecules of water. Another combustion reaction using propane and oxygen is C3H8 plus 5O2 reacts to give 3CO2 plus 4H2O. In this equation, one molecule of propane, C3H8, chemically reacts with 5 molecules of oxygen to produce 3 molecules of carbon dioxide and 4 molecules of water. Material balance. Material balancing is a method used by technicians to determine the exact amount of reactants needed to produce the specified products when two or more substances are combined in a chemical process. Reactants must be mixed in the proper proportions to avoid waste. Material balancing provides an operator with the correct ratio. A balanced equation is a chemical equation in which the sum of the reactants, atoms, equals the sum of the products, atoms. The steps in checking a material balance are 1. Determine the weight of each molecule, 2. Ensure that reactant total weight is equal to product total weight, and 3. Determine the numbers of reactant atoms. The number of atoms is given by numerical prefixes and subscripts. For example, 2H2 equals 4 hydrogen atoms. Weight can be expressed in atomic mass units, AMU1 AMU equals 1 gram, 1 pound, or 1 ton. AMUs are weight ratios, so the units can be anything you want. For example, check the material balance of this chemical equation. Hydrogen ion plus hydroxyl ion reacts to give H2O. Step 1. Determine the weight of each molecule. Hydrogen ion, 1 AMU, plus hydroxyl ion, 17 AMU, reacts to give H2O, 18 AMU. Hydrogen ion, 1 gram, plus hydroxyl ion, 17 grams, reacts to give H2O, 18 grams. Step 2. Ensure that reactant total weight is equal to product total weight. Step 3. Determine the numbers of reactant atoms to be sure they match. The reactant side of the equation has 2 hydrogen atoms and 1 oxygen atom. The product side of the equation has 2 hydrogen atoms and 1 oxygen atom. The equation is balanced. Determining whether a chemical equation is balanced can also be done by simply listing the reactants and the products and making sure the totals for each element are the same on each side of the equation. Na2O plus 2HOCl reacts to give 2NaOCl plus H2O. Reactants are 2 sodium, 3 oxygen, 2 chlorine and 2 hydrogen, and products are 2 sodium, 3 oxygen, 2 chlorine and 2 hydrogens. This chemical equation is balanced. Now, let's look at another equation. 2H3PO4 reacts to give H2O plus H4P2O8. Reactants are 6 hydrogen, 2 phosphorus, 8 oxygen, and products are 6 hydrogen, 2 phosphorus and 9 oxygen. This chemical equation is not balanced. When balancing an equation, the following principles and criteria are very helpful. Determine if the equation is balanced or not. Never change the subscripts. For example, in H2O, changing the subscript 2 will alter the composition and the substance itself. Focus on the coefficients in order to balance an equation. Work from one side to the other. Typically, it is easier to start with one side and then balance the other. Most operations move left to right, trial and error. Ensure that you have included each source for a particular element that you are attempting to balance. It is possible that 2 or more molecules contain the same element. Adjust the coefficient of monoatomic elements last. Adjust the coefficient of polyatomic ions that are acting as a group in self-contained groups on both sides of the equation. For example, this is not balanced equation, NH4, 2CO3 NH3 plus CO2 plus H2O, and this is balanced equation, NH4, 2CO3 reacts to give 2NH3 plus CO2 plus H2O. Reactants are nitrogen 2, hydrogen 8, carbon 1, oxygen 3, and products are nitrogen 2, hydrogen 8, carbon 1, oxygen 3. Each problem will present its own mystery, and most can be solved using the inspection method. You can try this yourself by balancing the equations shown in picture. Continuous and batch reactors. Industrial manufacturers use 2 basic methods of reactor operation, batch and continuous. In a batch operation, raw materials are weighed carefully and added to a reactor. The raw materials are mixed and allowed to react. After a predetermined amount of time, the batch is dumped, and a new batch is mixed. Continuous reactor operation adds raw materials incrementally to the reactor. Finished products flow out while raw materials flow in and are exposed to catalysts, pressure, liquids, or heat. Stirred reactors. A common type of reactor is the mixing or stirred reactor. The basic components of this device will include a mixer or agitator mounted to a tank. The mixer will have a direct or an indirect drive. The reactor shell is designed to be heated or cooled and withstands operational pressures, temperatures, and flow rates. The design may include tubing coils wrapped around the vessel, internal or external heat transfer plates, or jacketed vessels. Hot oil, steam, or cooling water may be the heating or cooling medium. The stirred reactor is designed to mix 2 or more components into a homogeneous mixture. As these components blend together, chemical reactions occur that create a new product. Blending time and exact operating conditions are critical to the efficient operation of a stirred reactor. Stirred reactors are equipped with a number of safety features: pressure relief systems, quench systems, process variable alarms, and automatic shutdown controls. Quench systems are designed to stop the reaction process. Pressure relief systems are sized to handle and contain any release from the reactor. The relief system may be designed for liquid, vapor, or a liquid-vapor combination. Safety relief systems allow process releases to go to the plant flare system. Sometimes a chemical scrubber system is used before a product is sent to the flare system. Process variable alarms will be activated by analytical, composition, pressure, temperature, flow, level, and time variables. Rotational speed on the agitator may be fixed or variable. A series of interlocks, permissives, and alarms will engage during operation and will provide a support network for the technician. A series of process video trends will be displayed to track each of the critical variables. Samples are taken frequently to ensure product quality. Stirred reactors are connected to off-specification (off-spec) systems that allow flexibility in switching between prime and off-spec situations. The automatic shutdown allows a technician to push one button and shut the unit down in the event of an emergency or runaway reaction. A stirred tank reactor is often referred to as an autoclave or batch reactor. This type of reactor is used in both batch processes, such as the suspension vinyl resins unit and the phenolic resins unit, and continuous feed processes, such as the solvent vinyl resins unit and the polyethylene unit. The basic features of a stirred reactor are designed to provide long reaction times, mechanical agitation, and a method of cooling or heating the reaction. Stirred tank reactors are used for liquid-liquid reactions, gas-liquid reactions, and liquid-solid reactions. Stirred tank reactors are used for reactions that require a relatively long reaction time and for reactions of slurry or thick liquid in which mechanical agitation must be used to provide a uniform reaction mixture. Such reactors are also used when the production rate is to be variable, and several different reactions or products are to be made in the same reactor. The early research and development of most processes is conducted in batch stirred reactors because of their versatility. Other considerations that must be taken into account are how much agitation is required to produce a uniform reaction mixture, what type of heat transfer equipment will be needed to prevent excessive fouling of the heat transfer surface, the minimum size of reactor that is needed to obtain the necessary reaction time, and whether a catalyst is needed to promote the reaction and how will it be added to prevent a localized reaction. Calcium carbonate. Calcium carbonate is often referred to as the world's most versatile mineral. It is often classified in the following groups: chalk, dolomite, limestone, and marble. Modern applications for calcium carbonate include adhesives, sealants, animal feed, carpet backing, concrete, plasters, fertilizers, pharmaceuticals, glass, ceramics, paint, paper, plastics, composites, rubber, and elastomers. A simple reaction used to illustrate the production of calcium carbonate is CaOH, 2 plus CO2 reacts to give CaCO3 plus H2O. Calcium hydroxide plus carbon dioxide produces calcium carbonate and water. As the CO2 is bubbled up through the calcium carbonate, a reaction occurs that forms an insoluble white precipitate, and the solution turns milky white. This reaction requires 74 parts calcium hydroxide and 44 parts carbon dioxide to form 100 parts calcium carbonate and 18 parts water. It is possible for a second reaction to occur if we continue adding carbon dioxide to the white solution. The chemical equation for this reaction is CaCO3 plus H20 plus CO2 reacts to give CaHCO3, 2. In this reaction, calcium bicarbonate is produced and the solution changes from milky white to clear. Alkylation stirred reactors. Alkylation units take two small molecules, isobutane and olefin, that is, propylene, butylenes, or pentalenes, and combine them into one large molecule of high-octane liquid called alkylate. This combining process takes place inside a reactor filled with an acid catalyst. Alkylate is a superior antinot product that is used in blending unleaded gasoline. After the reaction, a number of products are formed that require further processing to separate and clean the desired chemical streams. A separator and an alkaline substance are used to remove or strip the acid. The stripped acid is sent back to the reactor, and the remaining reactor products are sent to a distillation tower. Alkylate, isobutane, and propane gas are separated in the tower. Isobutane is returned to the alkylation reactor for further processing. Alkylate is sent to the gasoline blending unit. Sodium phosphate reaction. A common reaction used as the foundation for the production of sodium phosphate is 98 parts phosphoric acid H3PO4 and 120 parts sodium hydroxide 3NaOH produce 164 parts sodium phosphate Na3PO4 and 54 parts water H2O. Fixed bed reactors. A fixed bed reactor, often called a converter, is a vessel that contains a mass of small particles, usually 0.1 to 0.2 inch in diameter, through which the reaction mixture passes. The mass is usually a packed bed of catalyst, which promotes the reaction. The mass could also be column packing such as Raschig rings, burl saddles, or marbles. In this case, the packing creates more heat transfer surface to give better heat distribution in the converter. The bed of packing, whether catalyst or inert particles, is positioned in the direct path of the process flow and can be arranged as a single large bed, as several horizontal beds supported on trays, or as several beds, each in its own shell. It can also be in several parallel packed tubes in a single shell. As the process medium passes through the catalyst, the reaction occurs. Since the catalyst occupies a fixed position inside the reactor, it is not designed to leave the reactor with the process fluid. Fixed bed reactors are designed with an inlet line and an outlet line, catalyst bed limiters, distribution and support grids, catalyst removal hatches, process variable instrumentation, and safety systems. Many converters have a method of removing or adding heat from the bed. The main reasons for arranging the packed beds in a configuration other than the large single bed are to provide better heat transfer, to provide better distribution of the reaction mixture through the converter so that the gas or liquid feed will not channel through the bed, and to reduce the amount of force applied to the packing at the bottom of the bed. Several design considerations must be taken into account in constructing a converter. The free area of the packing must be great enough to allow an acceptable pressure drop through the reactor at the design feed rates. The packing must be strong enough to resist collapsing at design conditions over a reasonable length of time. If the packing is a catalyst, its active life should be long enough to produce production runs of economic duration. The design of the beds should provide for removal of the heat of reaction so that there are no hot spots in the bed. Hydrodesulfurization. Crude oil is a mixture of hydrocarbons, clay, water, and sulfur. Some crude mixtures have higher concentrations of sulfur than others. These high sulfur mixtures are referred to as sour feed. Hydrodesulfurization is a process used by industrial manufacturers to sweeten the mixture by removing the sulfur. During operation, hydrodesulfurization units use a fired heater, separator, and a fixed bed reactor. Sour feed is mixed with hydrogen and heated in a fired furnace. The heated mixture is sent to a reactor, where the hydrogen combines with the sulfur to form hydrogen sulfide. Lowering the temperature slightly causes the sweet crude to condense, leaving the hydrogen sulfide in vapor state. This vapor and liquid mixture is sent to a separator, where the low sulfur sweet feed is removed. The hydrogen sulfide and hydrogen are sent on for further processing, and the hydrogen is separated and returned to the original system. Hydrocracking. Hydrocracking is a process that industrial manufacturers use to boost gasoline yields. The process takes heavy gas oil molecules and splits them into smaller, lighter molecules called hydrocrackate. During operation, hydrocracking units use a first and second stage fixed bed reactor, a separator drum, and a fractionating tower. The hydrocracking process takes heavy gas oil feed and mixes it with hydrogen before sending it to the first stage reactor. The reactor is filled with a fixed bed of catalyst. As process flow moves from the top of the reactor to the bottom, the cracking reaction takes place. First stage hydrocrackate is sent to a separator drum, where the hydrogen is reclaimed and the hydrocrackate is moved on to a fractionation tower. In the fractionation tower, the hydrocrackate is separated into 5 cuts: butane, light hydrocrackate, heavy hydrocrackate, heating oil, and heavy bottoms. The heavy bottoms is mixed with hydrogen and sent to the second stage reactor for further processing. The second stage reactor reclaims as much of the hydrocrackate as possible before sending it to the separator and tower. Reformer, fixed bed, reactor. Reformers are designed to change low-octane naphtha into high-octane reformate. The gasoline your car runs off is composed primarily of naphtha. In this process, naphtha is heated up in a large commercial furnace to a specific temperature that brings the liquid to its boiling range. This heated vapor enters the top of a large, fixed-bed reactor filled with catalyst. When the catalyst and vaporized naphtha come into contact, the larger, low-octane molecules give up some of their hydrogen atoms and change into smaller, high-octane naphtha molecules. A separator is used to separate the hydrogen and high-octane naphtha. Fluidized bed reactors. A fluidized bed reactor suspends solids by the countercurrent flow of gas from the bottom of the reactor. Over time, particles segregate as heavier components fall to the bottom and lighter ones move to the top. During operation on a coal gasification unit, flows and temperatures are established before the bed is built. The reactor closely resembles a vertical distillation tower. Hydrogen gas inlet flows are mounted on the bottom of the reactor and must be controlled to keep from blowing the bed material over the top. A solids feeder is mounted a third of the way up the reactor. As the auger turns, coal is fed into the reactor. Methane gas is released during the run. Fluid catalytic cracking. Crude oil comes into a refinery and is processed in an atmospheric pipe still. The side stream of the pipe still is rich with light gas oil. Fluid catalytic cracking or CAT cracking units take this gas oil and split it into smaller, more useful molecules. During operation, fluid catalytic cracking units use a catalyst regenerator, a fluidized bed reactor, and a fractionation tower. Gas oil enters the reactor and is mixed with a superheated powdered catalyst. The term cracking is used to describe this process because, during vaporization, the molecules split and are sent to a fractionation tower for further processing. The chemical reaction between the catalyst and light gas oil produces a solid carbon deposit. This deposit forms on the powdered catalyst and deactivates it. The spent catalyst is drawn off and sent to the regenerator, where the coke is burned off. Catalyst regeneration is a continuous process during operation. In the fractionation tower, the light gas oil is separated into 5 cuts: catalytic cracked gas, catalytic cracked naphtha, catalytic cracked heating oil, light gas oil, and residue. Simple startup procedure for a fluidized cat cracker. 1. Ensure the air blower is running. The catalyst bed must be kept in a fluidized condition to control coking. 2. Circulate the heated catalyst between the reactor and regenerator. 3. Line up the feed, oil, to the riser. 4. Line up the reactor overhead vapor line to the main column. 5. Start the main column bottoms pump. 6. Start the overhead gasoline pump. Note that, after the main column overhead receiver level is established, the high volume of gases in the overhead receiver will be sent to a wet gas compressor. The wet gas compressor discharges to coolers where the gases are condensed for further processing. 7. Establish reflux and pump arounds for main column temperature control. Fluid coking. Fluid coking is a process used by industrial manufacturers to squeeze every last useful molecule out of heavy residues. Residue from other processes flows into a specially designed, high-temperature fluidized bed reactor. Light products vaporize and flow to a fractionation column. The remaining material is sent to a burner, where further processing takes place. The burner produces three products: coke or gas for use in the plant, product coke for sale, and recycled coke for the reactor. Tubular reactors. The design of a tubular reactor can vary from the simple jacketed tube to multi-pass shell and tube reactors. This type of reactor is simply a heat exchanger in which a reaction takes place. Tubular reactors are used for liquid and gaseous reactions. The raw material feed usually must be fairly cleaned, or it may plug the tubes. Agitation in these reactors, if any is needed, is provided by the turbulence of the flow of the feedstock through the tubes. Because the tubular reactor contains only a small volume of reactants at a given time, it is used only for continuous feed processes. The considerations in designing a tubular reactor are the heat transfer surface required to maintain the reaction temperature, the tube volume needed to produce the desired amount of reaction and production rate, and the tube size needed to give an acceptable pressure drop through the reactor. Tubular reactors are needed for chemical synthesis. Ammonia process. The production of ammonia is a popular process used by industry on a large commercial scale. The simple equation is 28 parts nitrogen N2 and 6 parts hydrogen 3H2 produce 34 parts ammonia 2NH3. This illustrates how nitrogen and hydrogen are passed through a tubular reactor filled with catalyst. Chemical synthesis. The purpose of the tubular reactor in chemical synthesis is to combine cyclopentadiene, CPD, and butadiene, BD, to form, synthesize, vinylnorbornene, VNB. VNB is the primary component added to a sodium catalyst and alumina to make ethylnorbornene, ENB, a special additive used to strengthen common rubber products. The equipment used during the operation is feed tanks, 3 pack towers, a continuous mixing reactor, a tubular reactor, and product tanks. During operation, a mixture of dicyclopentadiene, DCPD, and aromatic 200 is blended in a feed tank. The mixture is pumped through a preheater and into a fractionation tower. Toluene is added to the tower as a diluent. A reflux stream also enters the top of the tower and returns CPD, BD, and toluene. As the feedstock enters the pack tower, it cracks from DCPD to CPD. The heavy, aromatic oil stays in the bottom of the tower and acts as a temperature stabilizer. The overhead product is condensed and sent to a chilled mixing reactor. The product on the bottom, called bottoms, is sent to slop, which is best described as a product that is no longer needed for this process. However, it is often recycled and used in another process. In the continuous mixing reactor, chilled water coils maintain a low temperature. Butadiene enters the bottom of the reactor and mixes with the overhead distillate. The mixed feed is sent to a feed preheater before it enters the tubular reactor. The reactor resembles a shell and tube heat exchanger with 3 large tubes. The outer jacket is filled with hot oil that maintains a specific set point. A large centrifugal pump circulates the feed through the reactor as the synthesis reaction occurs. The reactor is mounted vertically, and flow moves clockwise through the tubes. Special inhibitors are added to the feed to limit the formation of insoluble polymer during operation. After the reaction occurs, a small percentage of BNB is formed. This mixed stream continuously flows through a reduced overhead line to a second tower. The purpose of the second tower is to separate and recycle the BD. This process is accomplished easily because of butadiene's lower boiling point. The prime bottoms product is sent to a third, vacuum, distillation column for product separation. In the third fractionation tower, the mixture is separated into 3 cuts: BD, CPD, and toluene, overhead, VNB, side stream, and bottoms. Reaction furnaces. Reaction furnaces are simply fireboxes containing an arrangement of tubing through which the reactant stream is passed. A fuel and air mixture is introduced into the brick-lined firebox, which provides the heat for the reaction that occurs in the tubes. Most furnaces are used to crack hydrocarbons. However, there are reformer furnaces in which steam and methane are reacted together to get synthesis gas, carbon monoxide and hydrogen. For the catalytic cracking of hydrocarbons, catalytic pellets are packed in the tubes inside the furnace. Notice that the raw material feed to the furnace is preheated by introducing the feed into the furnace through tubes in the vented stack. The hot vent gases heat the feed before it reaches the tubes, which are in direct contact with the flames of the burning fuel gas. Reaction furnaces are used in the olefins and vinyl chloride unit. General reactor design considerations. Besides choosing a type of reactor and the considerations associated with each type, there are certain design considerations that are common to all reactors. These factors include corrosion, safety devices, heating and cooling media, and instrumentation. At the operating conditions of some reactors, the reactants or products may be corrosive to the common materials of construction. Tests should be made on the reaction system if corrosion data of the system are not known. Corrosion can contaminate the product, inhibit the reaction, or poison the catalyst. Usually, any reactor or reaction system can have a set of conditions that could cause a hazardous situation if allowed to exist. Safety devices such as high-pressure relief valves and alarms, high-temperature alarms and emergency cooling, fire control systems, and toxic chemical detection systems are available for most hazardous conditions and should be installed as needed. The choice of the method for heating or cooling the reactor must be made in the design phase. The basis for such a decision is concerned with 1. The availability of steam, brine, cooling water, and the like, 2. The temperature at which the reaction must be controlled, and 3. The cost of each method per pound of production. Most operating personnel, if allowed to, would have a great array of instrumentation at their disposal to control and monitor a reaction system. On the other hand, many design engineers would like to place a minimum of elaborate instrumentation into a unit to decrease the plant investment. Somewhere in between, the unit obtains a sufficient number of instruments to operate the reactor in an efficient and safe manner. Instruments must be installed to detect and control reaction conditions such as temperature, pressure, feed composition, and flow rates. Other instruments are required to detect hotspots in catalyst beds, excessive pressure drops, and impurities in the feed or product streams. The type and quantity of instrumentation are usually determined by past data and experience and from research and development. Reactor systems. A common type of reactor is the mixing or stirred reactor. The basic components of this device will include a mixer or agitator mounted on a tank. The reactor shell is designed to be heated or cooled and to withstand operational pressures, temperatures, and flow rates. The design may include tubing coils wrapped around the vessel, internal or external heat transfer plates, and jacketed vessels. Hot oil, steam, or cooling water may be the heating or cooling medium. The stirred reactor is designed to mix two or more components into a homogeneous mixture. As these components blend together, chemical reactions occur that create a new product. Blending time and exact operating conditions are critical to the efficient operation of a stirred reactor. A reactor is a vessel in which a controlled chemical reaction takes place, depending on the reaction variables. The operation of reactor 202, for example, enhances molecular contact between four reactants: pentane, butane, liquid catalyst, and solvent. Feed to the reactor is controlled at 36.5 GPM. The feed composition from the column is 38% liquid catalyst, 61% butane, and 1% pentane. Solvent feed to the reactor is controlled at 68 GPM. The materials in the reactor are chilled to 120 degrees Fahrenheit or 48.88 degrees Celsius at 85 psig. The reactants are designed to form a new product with an excess of pure butane. A separator is used to remove the new product and isolate the butane for storage. The effective pressure on a reaction cannot be generalized as easily as the effective temperature. In a liquid phase reaction, pressure can increase or decrease reaction rate, depending upon the readiness of the reactants or products to vaporize. In a gaseous reaction, pressure forces molecules closer together, causing them to collide more frequently. Therefore, the higher the pressure in a gaseous reaction, the higher the reaction rate. The concentration of reactants in the reactor has a major effect on how fast the reaction will take place, what products will be produced, and how much heat will have to be added to or taken away from the reaction. A reactor is a device used to convert raw materials into useful products through chemical reactions. Heat, reaction time, surface area, concentration, pressure, flow rates, and catalysts and inhibitors affect reaction rates. Process technicians are responsible for establishing correct flow or feed rates to the reactor, ensuring correct temperature, pressures, and level, monitoring and controlling reaction rates, time, ensuring that specified mixing or agitation is occurring, and monitoring and maintaining auxiliary equipment. Reactors combine raw materials with catalyst, gases, pressure, or heat. A catalyst increases or decreases the rate of a chemical reaction without becoming part of the final product. There are 5 basic types of reactors: stirred tank reactors, converters, or fixed bed reactors, fluidized bed reactors, tubular reactors, and furnaces. Alkylation units take 2 small molecules and combine them into 1 large molecule. Exothermic reactions give off heat. Endothermic reactions absorb heat. Replacement reactions can be used to remove undesired products and replace them with desired ones. Neutralization reactions remove hydrogen ions, acid, or hydroxyl ions, base, from a liquid. Combustion reactions are exothermic reactions that require fuel, oxygen, and an ignition source and give off heat and light. In this type of reaction, oxygen reacts with another material so rapidly that fire is created. That's all, gentlemen. If you like my training course, please follow my YouTube channel Petro Intelligence for more courses. Good day and good luck.